You know, there's an entire world of engineering that's working tirelessly, completely out of sight, just to keep our world running. Today, we're going to dive deep, deep underground to look at one of the most critical, yet totally overlooked pieces of that puzzle, the coating on a pipeline.
It's a pretty simple question, right? But the answer is surprisingly complex. I mean, think about it. We've got this colossal network of steel tubes buried under tons of earth and rock, and they're carrying everything from oil to natural gas at super high temperatures and pressures. So what's stopping them from just tearing themselves apart? Just take a look at this. This is only a diagram of one small section. Now try to imagine this stretching for thousands upon thousands of miles, like a hidden circulatory system for our entire economy. And you got to remember, every single inch of that pipe is in a constant battle with physics, a battle it has to win every second of every day.
Okay, so let's dive into what that battle actually looks like. Because to really get the solution, you first have to appreciate the sheer power of the problem that every single one of these buried pipes is up against.
So, it all kicks off with a super basic law of physics: thermal expansion. Hot stuff flows through the pipe, right? That heats up the steel. And what does hot metal do? It wants to get longer. It wants to expand. But here's the problem. It can't. It's pinned down, buried under tons of soil that holds it in place. It's literally like stretching a rubber band to its absolute limit and just holding it there. That stored energy, that's called expansion stress. And if it gets too high, the pipe can fail, catastrophically.
So, how in the world do engineers manage this incredible stress? Well, your first line of defense is the pipe's coating. Now, you might just think of it as a protective jacket, and yeah, you'd be partly right.
At first glance, a coating's job seems pretty obvious. It stops the pipe from rusting, which is huge. It protects it from getting dinged up by rocks, it provides some insulation, and of course, it helps prevent leaks. And these are all absolutely vital functions, for sure.
But, and this is the really cool part, that's not the whole story, not even close. What's so interesting here is that the coating performs another, much less obvious job that might just be the most important one of all when it comes to stopping that crazy stress buildup we were just talking about.
And that is what brings us to the real unsung hero of pipeline engineering, a concept called the coating factor.
The coating factor is pretty much exactly what it sounds like. It's just a number that tells you how much friction, or let's call it grippiness, the coating has against the soil. Seriously, think of it like the tread on a tire or the bottom of your shoe. Some coatings are slick and smooth, while others are rough and they really grab onto the earth.
And wow, this table from the source material just lays it all out perfectly. It shows the coating factors for all these different materials. A rough concrete coating has a factor of 1.0. That's maximum grip. But then you look at a modern, slick coating like polyethylene, and its factor is just 0.6. That is a huge difference in grippiness.
Okay, to make this super clear, let's think about it like this. A concrete coating is like a heavy-duty hiking boot with these deep, rugged treads that just dig into the trail. A polyethylene coating, that's more like a smooth-soled dress shoe on a polished floor, way more likely to slip. So the big question is, which one do you actually want on your pipeline?
Well, of course, engineers don't just guess, right? They need proof. So to find out how much this grip actually matters, they put it to the test. The source material we're looking at details this really cool case study where they used powerful simulation software to get a real, definitive answer.
So what they did was, they took this typical pipeline route you see on the screen and ran a detailed stress analysis. They kept every single thing else, the soil type, the pipe material, the temperature, exactly the same. The one and only thing they changed in each simulation was that coating factor, testing everything from that slick 0.6 all the way up to that super grippy 1.0.
So what did they find out? What did this whole lesson in friction actually teach them? Well, the results were incredibly clear, and they really show just how critical this one little number can be.
Okay, check this out. The big reveal is right here in this first graph. Just look at that downward curve. As the coating factor along the bottom goes up, meaning the pipe gets grippier, the expansion stress on the side goes down, and not just a little, but a lot. More grip meant the soil could hold the pipe more firmly along its entire length, spreading out that expansion force, instead of letting it all build up in one dangerous spot.
And get this, it wasn't just about the stress inside the pipe. The second graph shows that as the grip increased, the amount the pipe actually moved at its free ends went way down. A grippier coating basically acts like a massive anchor, holding the whole pipeline steady against those immense forces that are trying to make it move. So,
That's it then, right? Simple. Just slap on the grippiest coating you can find and call it a day. Well, in the world of engineering, the answer is almost never that simple.
And this is where it gets really interesting. The researchers themselves point this out, and this quote is just key. They say that while a higher grip totally worked for this specific example, it might not always be true, because friction's effect is non-linear. What that means is, in a different scenario, say with different soil or more bends and curves in the pipe, that same high friction coating could actually grab the pipe in all the wrong places, concentrating the stress and making the whole problem even worse. The perfect grip isn't one size fits all. It depends entirely on the unique conditions of each and every pipeline.
You know, this whole coating factor thing is just a perfect example of these hidden variables, these invisible forces that engineers have to identify and master. It really makes you wonder, doesn't it, as you go about your day, what other unseen battles are being fought in the bridges you drive over, the buildings you're in, and all the networks all around us, all just to make sure our world keeps running safely.